Welcome, and thank you for standing by. All participants are in a listen-only mode until the question-answer session of today's call. At that time, you can press star 1 on your phone, unmute, and record your name. Also, this call is being recorded today. If you have any objections, you may disconnect. It's my pleasure to turn the call over to Katie Cousins. You may now begin, ma'am.
Thank you, Michelle. Hi, everyone. I'm Katie Cousins, a Public Affairs Officer at NASA's Ames Research Center in California's Silicon Valley. Welcome to today's media teleconference to discuss the landing site selection for NASA's first lunar mobile robot, the Volatiles Investigating Polar Exploration Rover, or VIPER, which will be delivered to the moon in late 2023 under NASA's Commercial Lunar Payload Services Initiative. We have 5 panelists joining us today. Before we begin, I will introduce each panelist and let them say a few words about today's announcement. We will then move to the question and answer session, accepting questions from media who dialed into the phone bridge. This media telecon will be limited to 1 hour. Today's panelists are Lori Glaze, Director of the Planetary Science Division at NASA's headquarters in Washington, Daniel Andrews, VIPER Project Manager at NASA Ames, Anthony Colaprete, VIPER Lead Project Scientist at NASA Ames, Darlene Lim, VIPER Deputy Lead Project Scientist at NASA Ames, and Daryl Gaines, Deputy Manager for NASA's Commercial Lunar Payload Services at NASA's Johnson Space Center in Houston. And with that, let's get started. Over to you, Lori.
Thank you so much, Katie, and hello to everybody. It's really my pleasure to speak to you all today to announce where the VIPER rover, NASA's first resource mapping mission on the surface of another celestial body, where it will be exploring near the moon's south pole. The data that VIPER is going to return from the lunar south pole will enable planetary scientists around the world to better understand our moon's cosmic origin, its evolution, and its history. VIPER also plays an important role in NASA's overall lunar exploration goals for Artemis, because once it's on the surface, it will search for ice and other resources on and below the lunar surface that could one day be used and harvested for long-term human exploration of the moon. The team at NASA's Ames Research Center deliberated on 4 potential landing site study areas. They carefully considered critical parameters, such as Earth's visibility for communications from the moon to the Earth, sunlight, terrain that's well-suited for the rover to navigate, and most importantly, of course, the expected presence of ice and other resources. While analyzing all of these constraints, one study area came out ahead of all the rest, maximizing science return and flexibility to help ensure mission success once VIPER is on the moon. And so it is my pleasure to announce that VIPER, NASA's first robotic lunar rover, will land near the western edge of Nobile Crater at the moon's south pole in 2023. Nobile Crater is an impact crater near the moon's south pole that was formed through a collision with another smaller celestial body, and the region near Nobile that VIPER will explore has a surface area of about 36 square miles, and about 10 to 15 square miles of that is what VIPER is expected to traverse during the course of its 100-day mission. This enigmatic region of the moon, which is more than 200,000 miles from Earth and one of the coldest areas in our solar system, has only ever been studied with remote sensing instruments, such as the ones on NASA's Lunar Reconnaissance Orbiter and the Lunar Crater Observation and Sensing Satellite, known as LCROSS. All of that will change once VIPER lands. The rover is going to get close and personal, up close and personal with the lunar soil, even drilling several feet down, which will truly help us redefine what we know about our moon by providing ground truth for interpreting all those remote sensing measurements. The Nobile region of the lunar south pole has places that the rover can visit which are almost permanently covered in shadow, which means it's cold enough for ice to exist. VIPER is going to be delivered to the moon in 2023 through the innovative Commercial Lunar Payload Services, or CLPS initiative, which you'll hear Daryl speak about in more detail in a few minutes. Through CLIPS and Artemis, we're truly embarking on the next chapter of lunar and planetary science exploration, and I cannot wait to see what incredible data VIPER is going to return once it lands near Nobile, and what amazing science it will yield as a result. And so with that, I thank you, and I'm going to turn it over to Dan Andrews.
Very good. Thank you, Lori. So the VIPER team is really excited to be at this point in our planning. We've been working very hard and doing a bunch of work to come to understand all the possible regions in which we could make the most of the science of this mission. The science that will come from the VIPER mission will bring great value to future Artemis missions and will really help inform the ability to sustain humans on the moon. If resources are plentiful and accessible, this could really change the nature of sustaining humans there, and also help us understand the nature in which to retrieve those resources. Like Lori said, we're going to the Nobile region on the moon. There's a number of different ice stability regions there, which is really important to us to understand where the ice is, in what concentrations, how deep, the nature of it, that type of thing, in order to help us steer to the science we want to conduct. Of course, the challenge in these ideal ice-bearing locations is they can be tough for a robotic rover to navigate. Just to give you a couple examples. Polar regions can be extremely cold in the dark, but also fairly warm in the daylight. And our little rover needs to be able to operate in both of those extremes and everywhere in between. Additionally, the sun is also very low on the horizon when you're in a polar location, you know, whether North Pole or the South Pole. The sun's very low on the horizon, and so lighting conditions can be very stark and the shadows very long. And so this makes it challenging for a rover and a rover driver to be able to have situational awareness about where the driver is taking the rover and how it's navigating. Finally, adding into all this is having the ability to be able to navigate through hills and craters, all while keeping the rover's solar panels pointed to the sun. We're a solar-powered mission, and so that's, of course, essential. So you end up needing a pretty capable rover with an operations team who's very adept at navigating through this very strange environment. So to actually conduct the science of the mission, we've defined these different types of regions, and we're conducting science stations there, which is where we think the ice might be found at various levels of depth on the surface and below. So VIPER will visit at least 6 different science stations where we'll use our 3 spectrometers to measure the actual ice concentrations and other resources, both above and below the surface with the help of our drill. So our drill locations will vary in depth and in location, of course, in these science stations, all with the purpose of revealing the nature, concentration, and type of entrained ice that could be in those regions. So in the end, VIPER's data will help scientists to predict where ice might be found, including in other places where the VIPER rover is maybe not going, effectively producing a lunar resource map. By characterizing key areas, we can have understanding about areas that maybe we don't even visit. So this is very powerful. So now I'm going to turn it over to Tony, who's going to tell you a little bit more about the rover traverse planning to date in this very interesting and challenging region.
Thank you, Dan. If I can expand on the picture Dan and Lori have begun to paint us. We have never seen anything quite like what we're going to see when we arrive at the South Pole. The moons of the pole, the poles of the moon are dramatic, especially the South Pole, where ancient impact basins have lifted mountains that dwarf Mount Everest. And as Dan described, a sun that just peaks itself over the horizon 5 degrees or so constantly creates shadows that literally run hundreds of miles long. It's going to be something that is truly out of this world. And as these shadows move and dance as we orbit the sun, opportunities for traversing are presented themselves through corridors of light and shadow. And it's these corridors of light and shadow that the VIPER rover will traverse and conduct its scientific investigations. Since we're solar power, we need to maintain sun on our panels except when we go into permanently shadowed craters. And indeed, we will visit several permanently shadowed craters, craters that have not seen sunlight for billions of years, to investigate inside of those craters, looking for volatiles, mapping out water. Viper, as Lori said, is really truly the first planetary mapping mission. It's meant to map. We're going to get a lot of mileage under our wheels in our 100-day mission. And in doing so, really be able to provide the first ever comprehensive map of the distribution of volatiles, water being one of those volatiles, distribution of temperatures and other environmental parameters that we think influence the presence of water, and the form of water that might be there. So the Viper mission at each of these landing sites as part of the evaluation process evaluated tens to hundreds of potential traverses. Here at the Nobile area, we evaluated hundreds of different traverses, settling on one that we have now as our baseline that travels approximately 25 or so kilometers in distance. As Dan said, visits at least 6 science stations, actually visits about 12 science stations, the current baseline traverse, and conducts tens of deep 1-meter drilling activities. Now, this is a baseline traverse. We've done this to get our planning going and understand and evaluate the site. But another aspect of a South Pole mission is that we are in constant real-time communication with Earth. And this provides an opportunity for unique discovery and reaction to the data that we take in real time that we just don't usually have in other planetary missions. So while we have this baseline traverse, we fully anticipate that it will evolve and change as we conduct the mission. We are going to be able to learn from our discoveries and react to those to actually optimize and extract even more science than we would have otherwise been able to do. And that's exciting. It's a very unique aspect of this mission. Not only do we get to explore one of the most dramatic landscapes there are in the solar system, but we get to react real time with the data and use that real time interaction to even better the observations and better the planning and traverse. And that's a real key aspect of this mission that I can't emphasize enough. Is truly unique. I'm going to turn it over to Darlene, actually, who leads the science operations for the Viper science team, to explain how we can take advantage of this unique capability, this real-time decisioning, and also talk a little bit about the variety of different science opportunities there are and some of the critical and complex questions that we hope to address with the Viper mission. So Darlene, I'll hand over to you to talk about that.
Great. Thank you so much, Tony, and hello, everybody. As Tony highlighted, Viper is truly it's a very exciting science mission, and we are very excited about it as well. Another element of the mission, as Tony spoke about, which will be very exhilarating to say the least, is its unique operational conditions. So the mission team will be operating the Viper rover from Earth in near real time, and the Viper science team will in turn have to be at the ready to provide timely near real time input, at very key moments, so that the science team can enhance the mission scientifically, intellectually, and to help optimize the mission science return overall. The Viper science team will be constantly synthesizing and analyzing instrument data from the rover at all points of the mission. And the science team, won't always have days or weeks to think on the data that comes in. Instead, the science team will have to react and make decisions that enhance the mission on a much faster minute-to-hour timescale. To get ready for this type of intense, very complicated, fast-paced work environment, our team has been very busy planning, innovating, and practicing together so that fundamentally we'll be able to provide the needed input to help, for example, as Tony expressed, optimize science return as we rove across the lunar landscape, or help select drill sites within the science stations of the Nobile region that will not only meet VIPER mission science objectives, but also provide very important ground truth data to the broader planetary and, of course, lunar science community. All of these quick decisions will be part of the science team's broader and long-term efforts to understand the factors that control the form and the distribution of water on the surface of the moon, as well as in the subsurface. And this is a top priority for VIPER. And so effectively, as the rover roves and sends back data, the team will be speaking with each other, collaborating, and working to answer such questions as, what are the dominant sources of polar water and other volatiles being substances that, particularly within the lunar environmental conditions, have the potential for rapid change? So what are they? And what are the retention, the loss, the mechanisms for transport of these, of the water and of the volatiles in the lunar south pole? And also, fundamentally, they'll be able to explore what type of processes have kept these types of volatiles of the water preserved on the moon for so long, or maybe not. And so all of the insights that we gain and the knowledge that we gain through the mission, this factors into not only informing the VIPER mission needs, but also it factors into addressing knowledge gaps that the lunar science, the planetary science communities have. And the really amazing thing as well to consider is that these data sets, this knowledge will provide foundational data for the planning of future lunar missions as well. But just to sort of take a step back to Earth for a second, before we can really get started, we have to first, we have to get to the moon. So to share more about this first leg of the VIPER adventure, I'll turn it over to Daryl Gaines. And he's going to talk about how our commercial vendor, our partner, Astrobotic, will deliver the VIPER rover to the moon. So over to you, Daryl.
Thanks, Darlene. So yes, we are so excited that VIPER, NASA's first lunar mobile robot, will be going to the moon in late 2023 in search of ice and other resources on and below the surface. Through the Commercial Lunar Payload Services Initiative, or CLIPS for short, NASA is buying lunar delivery services from American companies. The payloads we're sending to the moon advance capabilities for science, exploration, and commercial development of the moon, as you've heard previously. Science investigations and technology demonstrations will help NASA study Earth's nearest neighbor, Artemis, preparing us for human missions to the lunar surface. Working with more than a dozen or so American companies to rapidly expand the lunar economy and explore the moon, we're enabling a new and innovative approach to lunar deliveries in preparation for returning humans to the surface of the moon. And with that, I'll return to Kate.
Thanks, Daryl. Thanks, everyone. We'll now start the question and answer session. We have several reporters on the telephone bridge today. We'll need to limit everyone to one question. Once everyone has had a chance to ask one question, if time permits, we'll start from the beginning again. Our operator should identify you, but if not, please identify yourself and your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, push the *1 keys on your telephone to be placed in the queue. And with that, let's begin. Michelle?
If you'd like to ask a question, please press *1 on the phone. Our first question comes from Paul Brinkman with UPI. Your line is open.
Hi, yes, thank you very much. For Lori, I guess you indicated that the Nobile region provides the maximum science return and also flexibility. But can you just give a little more detail about why this region does that compared to other regions? We had heard a lot of talk about Shackleton Crater, I think. So I would just like to know what it is about Nobile that provides those benefits. Thanks.
Yeah, and Paul, it's really an excellent question, and I'm actually going to toss that one probably over to Tony to talk about a little bit, as it's his team that did all of the analyses. he and Dan Andrews. So perhaps Tony would like to speak to some of the constraints that led to that site selection.
Sure. Thank you, Lori. It's, as you can imagine, it's fairly complicated, complex, a lot of factors that were considered. And certainly areas near, in and around Shackleton were considered. As Lori pointed out, there's really four principal pieces to the puzzle. First is we need direct Earth communications to Earth to operate. We're not relying on a relay satellite, but direct to Earth communication. We are a solar-powered rover, so we need sun for at least most of the time. Obviously, we're going into shadowed craters, so we can operate in shadow. That's key. We need to have trafficable terrain. That primarily means slopes that are, less than a certain amount. We can't drive over things that are too steep. And then, as Lori pointed out, most importantly, there had to be some association with areas that are expected to potentially hold water. And we really don't know where the water is at the scales we're operating at. I call it the human scale. When we're down there on the moon, working at scales that you and I are more familiar with than orbital scales, we really don't know where that water is. So we had to find a place where we could cover significant distances. And by significant distances, I mean tens of kilometers, going in and out of thermal regimes that included everything from permanently shadowed craters with literally 50 Kelvin temperatures to areas that transitioned to a balmy 110 Kelvin, and then all the way up to 250 Kelvin. We want to study the entire range of thermal environments so we can build a correlation that we can extend globally. We didn't want to go to just a spot and understand that one point in by itself. We wanted to broadly understand a range of environments on the moon. The Nobile region offered that. It's up high on a massif, a big mountain range. So it's up very high, making communication with Earth actually very good. It's more towards the near side of Earth than, say, Shackleton is. It has a number of very old, fairly large PSRs. They're about 500 to 800 meters across. They're fairly big, and maybe 3.5 to 3.7 billion years old. So they're very old. That gave us a lot of opportunities to actually study this range of thermal regimes I mentioned. And then lastly, and very importantly, there's a number of areas on ridge lines nearby where nighttime shadows, every lunation, every 28 days or so, when the Earth sets, we lose communication. And the sun can set as well, potentially. In these regions, there's areas that only receive less than 50 hours of shadow, very short periods of shadow. That's something our rover can survive on batteries. So while the Earth sets and we can't have communications, we have to stop. We can park it in one of these areas. We call them safe havens. And Nobile had a number of these for us to choose from, which gave us a lot of traverse options. And so it came down to, as Lori described early on, a breadth of flexibility. There was an opportunity for 100+ day missions where we can visit a number of significant permanently shadowed regions and get tens of kilometers of traverse on our wheels. So that's why it just rose to the top as the most favorable site.
Our next question comes from Alexandra Witz. Your line is open.
Hi, this is Alex Witzy with Nature Magazine. My question is for Lori Glaze. So given that we don't know precisely where the water is or whether there even is water at Nobile, what is NASA doing specifically to get more information ahead of the 2023 landing? And specifically, could you address whether or not Lunar Trailblazer launch might be moved up?
So that's a great question, Alex. And the bottom line is that the primary goal here is to get the ground truth to help support interpretation of of the remote sensing information that we have in hand. We have some amazing remote sensing data already in hand from prior missions, from Lunar Prospector and from LRO and from LCROSS. And we have, I think, a tremendous data set that can help us at least identify places where we think we have the highest probability, and then with VIPER be able to do this mapping. So we're not even necessarily just going to one place and hoping that it has the ice there, but actually mapping out that area and doing the selective drilling to try and get the ground truth to compare with the remote sensing data. And that's going to be helpful and useful regardless of whenever the next remote sensing mission flies. And yes, I do think Lunar Trailblazer is going to provide some amazing data. At this time, the most reliable launch for Lunar Trailblazer remains on IMAP, which is where it's supposed to be a ride share. And that will be after the VIPER mission.
Our next question comes from Mike Wall with Space.com. Your line is open, sir.
Thank you for doing this. And this one's probably also for Lori, actually. And well, I mean, Tony first, and then maybe like the second part of it over to actually Lori. So what were the other 3 finalist sites, and could you just kind of characterize them a little bit, Tony? And then, like Lori, could you maybe say if these are going to be target sites for like future NASA missions to the moon or for future Artemis kind of work? Yeah, could you just kind of lay out what those other sites were and what NASA might want to do with them in the future? Thanks.
Sure, I'll take that first part. There were 4, as Lori put it, finalists. We actually considered probably about 15 different regions that we began our study on. The 4 finalists, I would say, were Nobile, the Nobile region, of course, an area just outside the rim of the crater Haworth, which is between Shoemaker and Cabeus. A ridge line that connects Shackleton and Des Garages, and that's often you've seen this particular piece of real estate described a lot. And then an area near Shoemaker Crater, which was one of my favorites, but turned out to be too cold and dark. So each of these areas had the qualities I described. Accessible thermal regimes, meaning, we could see places where we expected surface frost to near surface ice to totally dry. We need to study the dry as well to understand the whole picture. They had all these things. They had direct Earth comm. They had persistent sunlight over periods of time, and reasonably good traversable slopes. Ultimately, it came down to total number of working days. And by a working day, I mean days where we had both sun and comm on our rover. And we needed at least about 10 or so days to fulfill our mission requirements, just 10. We get plus 40 plus at Nobile, and it was much greater than any of these other places. So we were, it again provided that extra flexibility. But each one of those areas is a excellent location for further exploration, in my opinion.
Yeah, and I'll just second. I mean, Tony gave a great answer, so I'm not sure how much I can add other than to say, yes, all of the sites that they started to explore all have really great scientific value. The selection here, the down select down to those final 4, and then in the final selection is really based on the specific constraints for this mission. So other missions, you could imagine in the future if a future lander had a longer surface lifetime, multiple lunar days might change how we approach where we want to go. The ability of, at some point, if there is a communications network at the moon at some point in the future, and we're not relying on direct-to-Earth communications, that would also kind of change that parameter space. So the science at all of these is great, and they're absolutely in the mix for future missions.
Thank you.
Our next question comes from Leonard David with Inside Outer Space. Your line is open. Our next question comes from Leonard David with Inside Outer Space. Your line is open. Our next question comes from Jeff Faust with Space News. Your line is open.
Good afternoon. Just curious why you selected a landing site 2 years ahead of the launch. What was driving that, and what will you be doing in the 2 years leading up from now up until the scheduled launch? And then also, were there any landing sites that you considered but had to rule out because they were deemed not accessible by the astrobotic lander? Thanks.
That might be a good question maybe for Dan or Tony as well.
I was going to say Dan should take the first part at least about the 2 years ahead maybe.
Absolutely.
Can you repeat the first part? That was a combo question. I lost the first part.
Sure. The question is, what will you be doing? Why select the landing site 2 years in advance? And what will you be doing between now and the actual 2023 landing?
Got it. Yes. So as you can imagine, when we tell you that we have picked a particular region, the Nobile region, there are many, many permutations that we need to explore to try to get as much science out of the time that we have for this mission. And of course, I think it's understood that the time that we have with a solar-powered rover is limited because of the natural seasons of the polar regions of the moon. And this entire region will fall into darkness after, say, 4-ish months or so. And so we have a finite amount of time to get this mission done. And so we really want to optimize where we go and how we go about doing it, in combination with what you've heard already from a couple of the different speakers, including me, about the nature of Earth falling out of view periodically, naturally. And so we can't drive the rover when Earth is out of view, and the natural sun conditions and so forth. I can tell you in the most recent studies that we've been doing about the Traverse, we have been looking at a number of different ways we can navigate in and around permanently shadowed regions, while also making sure we arrive at safe havens, which you heard Tony describe earlier, so that we can make it through that period without having any communications to Earth. You can imagine that if there really are about 3 principal safe haven regions in the Nobile region that we're going to, which one do you head out for first? Which permanently shadowed region do you focus your efforts on day 1, lunar day 1? Or do you push it off to lunar day 2? All these things require time for us to explore and trade them against the capabilities of the rover, like I said, to lower risk and maximize science going forward. Tony, did you want to add anything to that?
No, I think you answered it very well. There's a whole lot more planning to go, even though we have our area. You know, we have not selected the specific lat long and the landing site. There is one for the baseline traverse, but as we move forward, what we look at is literally planning the traverse down to the drive segment detail, you know, down to the meter scale, which, you know, as high fidelity as the data allows, which is about a 1 meter scale. So we'll continue to plan on that, and as Darlene described, really develop the methods, procedures, and operations to perform in this real-time, high cadence, science cadence environment. So picking it now gives us the time we need to really prepare for the mission in 2 years.
As a reminder, if you would like to ask a question, please press *1 on your phone. Thank you. Our next question comes from Leonard Davis with Inside Outer Space. Your line is open, sir.
If I just learned how to use this Princess phone, I'd be there before. Because you're kind of flying blind in a way, and the suspect areas that may or may not have ice, is there any? What's the ability of Viper to if it does find ice, to actually understand the concentration and the layering and that kind of thing, because all that has to do with eventual processing and use of that ice. How is VIPER set up to really understand the constituency and what kind of ice layering you may be dealing with?
Well, I can take the first part of that. This is Tony, and then Darlene, I can hand it to you to expand. That is one of the principal questions that VIPER is after. So Dan mentioned we have 3 spectrometers that are on continuously while roving. And that's actually something really cool about this mission, in my opinion, is our prospecting instruments are on all the time while we're driving. Between science stations, they're on. In science stations, they're on. While drilling, they're on. These prospecting instruments, one is a neutron spectrometer. It has 2 channels and allow us to tell us the amount of hydrogen to about 1 meter deep and the depth to which the hydrogen is buried. Along with that, then we have a near-infrared spectrometer that tells us everything about superficial water ice, and then also a mass spectrometer that tells us about any gases that are coming up off the soil, either from being disturbed by the rover wheels or warmed or whatever. And so those are on continuously mapping out subsurface hydrogen and superficial hydration. There's enough information there to tell us if it's bound water ice or if it's granular water ice, etc. And then when we drill, in each science station, our requirement is to drill at least 3 times to 1 meter. We pull up 10 centimeter, what we call bites, 10 centimeter segments. We pull up one at a time, and we examine those with the near-infrared spectrometer and the mass spectrometer. And the beauty of that is one is looking at the solid form of any volatiles are there. That's the near-infrared spectrometer. And the other, the mass spectrometer, is looking at the gases that are coming up as those ices sublime once they're exposed to the vacuum of space. So between the 2 of those instruments, you have this wonderfully constrained observation of the volatiles as a function of depth. And we've tested this in the laboratory in thermal vac chambers at Glenn Research Center probably about 6 times, I think, over the years with the actual drill and the actual instruments. And it's a wonderful, simple way to actually profile with depth in 10 centimeter bites the distribution of water. That drill then, that ground truth, can then be applied to all the neutron data we've been gathering as we're driving. So the neutron data, as I mentioned, gives us both the total hydrogen and the depth, but it doesn't tell you the kind of hydrogen. Is it water? Is it methane? Is it bound or is it not bound chemically? What is the actual burial depth? By drilling, you basically provide a ground truth for all that extensive, aerially extensive neutron data. It's basically a technique we use with the USGS when they're mapping out a mineral deposit on the Earth. Drilling is expensive, even on Earth, so there's a lot of clever ways you can use limited diffuse drilling sets with prospecting data to characterize the overall distributions, and we're basically doing the same thing. Darlene, you want to add anything to that?
Sure. Yeah. Just to build on what Tony was saying, so even to back up a little bit more outside of this mission itself, like every time that we will go into a process of understanding, we're also building on decades of work from the planetary science community. And so our science team, has an incredible breadth of understanding of what has been done in terms of research, what they are doing currently, for example, in thermal modeling, in other kind of geochemical aspects and so forth. And they're going to bring all that into their day-to-day work life when we are actually on the moon. And so fundamentally, the way that we will get to understand the data that is coming in is that we'll take that foundational knowledge, we'll take the data as Tony was describing that's going to be coming in from all of these complementary instrument payloads, and then we'll put that together in our understanding of how what we're seeing will actually answer the questions that have been put forward by by this mission team, by the planetary science community, and then we'll break it down into its component parts and work through answering and, getting to a certain point where we feel comfortable with those particular inferences so that we can then make decisions moment by moment and then on longer timescales as to whether or not we feel that we're really, optimizing the science return from the mission and where we want to put the drills, for example, to really make sure that we're answering the questions to the best of our ability. So there's all sorts of complexities we bring together, and there's a heritage of knowledge that then serves forward to provide, a greater understanding for our team as we go along the process of interpreting and forming these resource maps as Tony was describing.
Great. Thanks very much.
Our next question comes from Kenneth Chang with New York Times. Your line is open, Mr. Chang.
Hi, thanks for taking my question. So you were saying that drilling is very expensive. If I'm not mistaken, the cost of the mission is about $650 million between the rover and the launch vehicle. And given that cost, wouldn't it make sense to fly this after Lunar Trailblazer?
So the costs that you're describing there include, as you said, the rover itself, as well as the delivery service, which is through CLIPS. And that delivery service includes the lander and the launch vehicle. And as I said earlier, this is really a ground truthing mapping, resource mapping mission. And the data that we have are very good at helping us to identify those high probability sites where we might find ice. We also have modeling to help us to understand where that ice might be, not just horizontally, but with depth. Yes, I do think that Lunar Trailblazer will add to that collection of knowledge, but I think we have absolutely sufficient knowledge to fly the Viper mission right now. And I think Dan has something he'd like to add as well.
Yeah, thanks for the question. It's a good question. So what's important to remember about Viper is that it has made an estimation of what it suspects would be the areas in which ice of different forms would exist and, frankly, might not exist, probably won't exist, like out in sunny dirt areas. And so we've divided the problem space into 4 chunks. We call these ice stability regions, right? There's surface areas where we think water ice might be stable, probably only in permanently shadowed regions. There are areas where it's probably in just the first 50 centimeters of the surface, maybe the second 50 centimeters, down from 50 to 100 centimeters or a meter. And then those areas where we don't think water ice would be stable probably at all in the first meter. The beauty of the way the mission's been laid out is when we go and conduct a mission, we don't have to be right. If the data shows that the way it needs to be thought of is differently, then we'll let the data speak to us and we might adapt the mission and go ahead and do things differently, but we're ground truthing it. And so we start with an initial premise, but the mission will tell us what we're finding, and in either case, this will be very useful for anything that comes along later. And what I'm thinking about later is, as a function of what Viper discovers, you can imagine there might be some technology demonstrators that might want to come along after that point to actually attempt to harvest some of the resource as a function of where we find it. And of course, that's where economics come in and a bunch of other facets as to where would be the ideal place to be able to harvest the resources. So I think now is the right time for a Viper-type mission to come along and build on what's already known, carry the ball forward to really define, as Tony said, meter scale of what's happening, and then give enough time for the follow-on work to be put in place so that ultimately we have a whole means of being able to harvest the resource if it's there and if it's economical in the future.
Our next question comes from Ken Kramer with Space Up Close. Your line is open, sir.
Hi, thank you for doing this. My question is about. I want to follow up on the science instruments. So you said you have a couple of science instruments. So I'd like to know how will you deliver these drill samples to the instruments to determine the composition in the water there. And what is the lowest percent composition of water you can detect? Thanks.
Yeah, I can take this one. This is Tony. So the drill we're using is called a percussive auger drill. And at the very bottom portion of the drill bit, the stem, is 10 centimeters of what we call biting flutes. So the drill flutes there have a different pitch so that they grab onto the sample and carry it with it. Rather than just moving the material up and out of the hole, it actually holds onto it. So what we do is actually we go down 10 centimeters at a time. We drill down 10 centimeters, then retract the drill, and at the about 10 centimeters above the surface, there is a passive brush system that brushes the drill cuttings off of those biting flutes into a chute and down onto the surface below the rover. So that's the extent of the sample delivery. Now, what we've done is we've positioned special sunshades so that when we drill, the underside of the rover is completely in shade. And so the drill cuttings are actually completely in shadow. And so then the near-infrared spectrometer and the mass spectrometer can view these cuttings 10 centimeters at a time be deposited onto the surface. And at each 10 centimeters, it goes back down, so 10 to 20 to 30 to 40, and it brings each of those bites up and brushes them in front of the spectrometers. After each brushing, we sit and we wait 5 minutes or so, watching the signal, the water ice and the water vapor, evolve. It slowly disappears over time. We've demonstrated this in thermal vacuum chambers, this technique. And so it's a very simple yet powerfully effective way to actually identify the volatiles in the subsurface cuttings without having to have complex capture mechanisms for the sample. We can actually then also, based on the geometry of the cuttings pile, one of the instruments, the Nervus instruments, has a camera on it that provides context for all the other spectrometers. It looks at the cuttings pile, images it continuously while we're making observations. We can combine the geometry of the pile with the observations from the near-infrared and mass spectrometers to actually get at the absolute concentration within the cuttings pile. This is both done analytically or theoretically, but also empirically. We've done a number of tests in laboratories, as I mentioned, where we can get nice relationships, very repeatable relationships between the amount of water in the cuttings pile and what the instruments see. In terms of sensitivity, we can sense well under 0.1% by weight water ice concentration, and the mass spectrometer down to tens of parts per million water concentration of water vapor. So we're very sensitive.
Wow, that's great. Thank you.
Mm-hmm.
Our next question comes from Issam Ahmad with AFP. Your line is open, Issam.
Oh, hi. Thanks for doing this. Can you hear me? Hello? Can you hear me?
Oh, yes, sir. We hear you.
Okay, great. My question was, if you could, it's a little basic. Could you sort of just characterize the differences between this rover and the other sort of the Mars rovers that NASA runs? Obviously, this one isn't autonomous; it's driven, piloted remotely. Has there been a previous lunar rover for NASA which wasn't driven by a human during the Apollo missions? And how fast does it go? How big is its drill? That kind of thing.
So this is Dan. I'll field this one. So lot to unpack there, but all very good stuff. So let's start with the Mars angle on things. When you see an image, if you haven't yet seen an image of the Viper rover, you'll notice it looks quite a bit different than what you're used to seeing on Mars. That is not an accident. The nature of how Viper has to operate and is constrained being a solar-operated rover in a non-atmospheric environment where sun is really low on the horizon and where we got to keep the solar rays on the sun as much as possible means the way we have to move has to be different than the Mars rovers. So the Mars rovers are designed in what's called by roboticists a rocker bogie system, which is that six-wheel system where two of the wheels on each side rock back and forth. The Viper rover actually has more motion capability to it. It's four wheels, but each of those wheels have independent active suspension and steering. So you can crab walk, you can move sideways while keeping the solar rays on the sun. What it really allows you to do is decouple the science you're trying to conduct from being able to stay powered facing the sun. Now, we do have a battery, so it isn't that if we go in the shadow, we lose power. As Tony had noted, we have 50 hours of the ability to just operate off of battery. However, we'd like to keep the batteries as charged as possible. So the idea that we could stay on the sun and charge while we're doing our business independent of our relative orientation, well, that's huge. That's a giant benefit for the mission. So that's one reason that they look different. And then, let's see, the drill, as you heard Tony mention, is 1 meter long. And that length was determined to be kind of an economic breakpoint. If you go down 2 meters, which might be interesting to see as well, you start to get into the regime where pulling out water volatiles, ice volatiles from that far below the surface actually starts to become difficult, quite difficult and expensive. And so we're trying to understand in the first meter, everything from the surface down to 1 meter below, and those 4 chunks that I described earlier, those 4 different regimes, what's there? What's really there? And does it vary with location, with sunlight, with a number of other features? And then really attempt to exploit that going forward. Did I answer all your questions? You had a bunch there.
Yeah, do you know the speed?
Yeah, so the funny thing about the Viper rover is compared to a car, it moves pretty slowly. Compared to any of the Mars rovers, it's twice as fast. So we have 2 different speed regimes, if you will. You heard Tony talk about earlier that we're taking science measurements all the time. That's at 10 centimeters per second linear speed, okay? So we can operate all the instruments, obviously not the drill while we're moving, but we can operate all 3 spectrometers at 10 centimeters per second and lower. Most of the Mars rovers operate at around 5 centimeters per second. But we also have the ability to do what we call rails driving, but it's our top speed where we're just trying to get from point A to point B. And we're not necessarily interested in conducting science, we're just trying to get somewhere. And that speed is 20 centimeters per second.
Great. Thank you very much.
You bet.
Our next question comes from David Dickinson with Sky and Telescope. Your line is open, David.
Yes, thanks for taking my question. I'm curious, and I think part of this was answered earlier during Ken Kramer's question. Is there any kind of imaging system beyond the science? I know you talked about the nervous system has a context camera, but are we going to be seeing any kind of like wide panoramics or anything like we see with Perseverance and Curiosity? Thank you.
I'll start and give you a quick landscape around the imaging systems of it, and then Tony, you, Darlene, feel free to jump in to provide more details if you like. So first of all, the rover itself, being that nobody has ever been in this polar region before, and given that stark contrast I was describing earlier, imaging is critically important for any rover, and especially for the Viper rover. So what we basically have are navigation cameras up on the top of a mast that are able to pan and tilt. And that's our primary means for judging where we're going and any obstacles and that type of thing going forward. And we can take panoramas, we can use it to calibrate where we are to offset any errors like slippage and that type of thing. So that one's very, very important. It's a stereo pair so that we can actually take some usable, quantifiable measurements. We also have stereo pair cameras located around the other sides, the aft and left and right sides of the rover. So we have the ability to do stereo vision out in all directions around the rover. Finally, we also have hazard cameras, and those are specifically located in the vicinity of the wheel wells of the rover. And as you can imagine, those could be critically important when we find that the rover is not moving the way we thought it would. Let's say we're abutted against a rock and it's tucked underneath, so it's hard for the navigation cameras to see it. We'd like to have a really great view of what's going on there. Maybe we're in a hole, maybe we hit a rock, maybe something's gone bad with a wheel. That's going to be invaluable intel should we find ourselves in that situation for making judgments about what to do going forward at that point. We got one of those in each of the 4 wheel wells. And then as Tony mentioned earlier, and then I'll be done, there's also imagery that's gotten right off of the instruments themselves, which could be used both for scientific and other purposes. Tony, Darlene?
Yeah, thanks, Dan. Just to build on Dan's statement, additionally, for us to when we think about the imaging systems on board of Viper, on board of the rover, we also like to think about their applications. So, of course, as Dan mentioned, there are navigational applications, and then there are further applications to science, because as we look out on the landscape, whether that's from the nav cam or the app cam or the hazard cams, we can put all that together into, for example, panoramas or into images that cover a smaller field of view. We can also use the imaging system, for example, on Nervous, in order to look at the drill as it's actually being deployed. So there are all sorts of important utilities and use cases for these different imaging systems, and they'll be very powerful tools for the science team to really enhance and embellish their understanding of the instrument data that's coming back. So again, you kind of get the theme that there is this, each of the different constituent parts of the rover really adds value to the other parts, and then we can derive a much more holistic view of the moon, and then our interpretations tend to be much more sound from there.
We have time for one more question, and the last question comes from Alexandra Witze. Your line is open.
For taking another one from me. Given that there's not that much knowledge about precisely where the ice is in this region, I wanted to ask Tony Colapri to say, what are the odds you don't find any ice at all?
Oh, I don't think I want to place out odds at this time. But this is exactly why we're going. Is we know there's water ice there, and we know some of it is at the surface and some is below the surface. Exactly where and how much and how it's distributed between the surface and subsurface is a large unknown. We think we understand some of the principal parameters that control its persistence, like temperature, and we think we know possible sources, like from the solar wind or cometary or volcanic input, but we don't know for sure. So Viper's going to go there and explore even in areas where we expect there not to be water, because that's important to test our hypothesis there. We don't think there's going to be water at this location, in this location. We better test that. And that's what we're doing, whereas we expect water to be present here, we're going to test that. If we find that and there's no water in any place we look, that is a fundamental discovery, and we will be scratching our heads and rewriting textbooks again, because it's just not something that we would expect, given the locations we're looking at. As I mentioned, we're very sensitive to very small amounts of water. So when I say not find water, I mean we really don't find water. Whether or not we find water that is insufficient for resource exploration, that's a whole nother question into itself. And just how much water is really required, et cetera. So I would say, regardless of what we find, the finding is going to be fundamental in terms of understanding the emplacement, retention, and history of water on the moon. We have that basic fundamental set of questions that any new information is going to be enlightening beyond what we have right now.
Thank you, Tony. That concludes today's News Telecon. I'd like to thank the panelists and our operator for their time today. I would also like to direct everyone's attention to nasa.gov/Viper, where we released the full story. Lastly, media who RSVP'd to this telecon will receive a link to B-roll. If you joined this telecon late, or if you would like to listen to it again, you may do so by dialing 888-566-0094. Again, that number is 888-566-0094. The recording will be available 1 hour after this call ends and will be accessible for 30 days. Thank you all again and have a wonderful day.
That concludes today's conference. All participants may disconnect at this time. Thank you for joining. Speakers, please stand by.